right, so our last lecture in Chapter 19 in Learning Unit 7 on kind of complex ionic equilibria is kind of building a little bit on this concept of sparing solubility of salts or ionic compounds. And so one of the things we'll talk about today is we sort of have a tell if we've sort of gotten past the equilibrium point with this kind of a situation, because we're talking about either something that's soluble in solution or not soluble in forming a precipitate. So we're going to talk about some ways to qualitatively be able to predict whether or not a precipitate will form, and actually doing some quantitative pieces to actually predict at what concentration would we need to be at in order to initiate that precipitation. So again, a few homework problems that will allow you to practice and reinforce some of the concepts we're going to talk about today. So just a concept to review that we've talked about before that has applicability for today is really this concept of thinking about Q versus K. And that was first introduced in Chapter 17. And remember that Q kind of represents a snapshot of where we're at. What are the concentrations that we are at right now? And then K represents the equilibrium concentrations. And so when we're thinking about a salt here or something that has sparing solubility, this Q versus K has to do with whether or not we have ions in solution that are completely soluble, or we've sort of exceeded the maximum solubility, in which that case we're actually going to have a precipitation. So again, the three options that we'll see for Q versus K are the same that we saw in Chapter 17. So if our concentrations that we're at are kind of the allowable concentrations, the maximum solubility that we'll have, in that case, we're going to say that the solution is at equilibrium. We wouldn't have any additional precipitation that would happen because we have the maximum allowable ions in solution. If Q is greater than K, we define that in Chapter 17 as product overload, which means that the equilibrium would shift back to make more reactant. And remember, in these equilibria, that reactant is really a insoluble salt, the solid salt. So again, that means we are going to decrease our solubility or initiate the formation of a precipitate. If Q is less than K, that actually means we used to call it reactant overload, but that it means that we still can fill up more ions in solution. So we actually still have the ability to have more salt come out of the solid kind of precipitate phase and into solution. So again, hopefully this will make sense as we walk through a few problems here. So again, a lot of these problems, I'm going to set them up for you, and then I'll ask if you want to sort of pause the video and try to work through them on your own. So this first problem here just kind of gives us a prompt. It says a common laboratory method for preparing a precipitate is to mix solutions that contain the component ions. And you may have had a lab in Gen Chem 1 that sort of did this situation, where you had two solutions that were made from completely soluble salts, but then when you mixed them together, there was the possibility of new pairings that maybe allowed for a precipitate to form. So for example, over here, we've got a solution of calcium nitrate. They tell us we have 100 milliliters of a solution of calcium nitrate. One of the things that you need to make sure that you're comfortable with, in Chapter 4 in Gen Chem 1, we had that table that kind of was the predicted solubility rules. And we gave that to you in Gen Chem 1, but I know I told everybody in Gen Chem 1, keep in mind you're going to have to know this table in Gen Chem 2. So kind of start thinking about it. And one of the things that's important to remember is that all nitrate salts are soluble. So if we've got a solution of calcium nitrate, what that really means is all of that calcium nitrate dissociates to make calcium ions and nitrate ions in solution. Remember that nitrate ions really represents spectators, not only from a precipitate sort of standpoint, but also from an acid-base potential. Nitrate's kind of a classic spectator ion. On the other hand, on the other side here, we're going to have a 200 milliliter solution of sodium fluoride. Again, remembering that all sodium salts are soluble, this salt completely dissociates into sodium cations and fluoride anions. Like the nitrate is a spectator ion, sodium is a spectator ion when it comes to precipitate formation as well. And as we learned a little while ago from a salt and a pH standpoint, sodium actually would not contribute to anything with pH either. Okay, so we have two solutions that are completely soluble, and we're going to mix them together here, and then we're going to ask, are there new pairings that we could have? So we did this qualitatively in Gen Chem 1 in Chapter 4. And you remember, when we had all of these guys in solution, we would say, well, here's our two spectators, nitrate and sodium. You're never going to have two cations interact anyway, but we have the potential for a new pairing between a cation and an anion here. And in this case, calcium and fluoride could form an insoluble salt. And so if we were doing this problem in Gen Chem 1, we would have just said a precipitate would form. Well, now we're going to delve a little bit deeper, and we're actually going to think about this from a quantitative standpoint, understanding that, well, calcium fluoride isn't totally insoluble. There's only a small amount that can exist in a dissociated state, but it's not zero. So the question asks us, will a precipitate form when we mix 100 milliliters of 0.3 molar calcium nitrate and 200 milliliters of 0.6 molar sodium fluoride? So thought of another way, once we've got these calcium and fluoride ions in solution, what we really want to know is, are these concentrations greater than the amount that will be allowable? There is some allowable amount of calcium and fluoride ions in solution, and now we understand the work that we could do to figure out what those concentrations are. So I'm going to give you two possible ways to solve this problem. I'm going to walk through them on the next slide, and then I'm going to ask you to pause the video and try working through one of them on your own. I'm going to work through both of them following a pause in the video, but I'd like to see if one of them makes more sense to you and you feel like you can see the solution and work through it. So again, two potential ways to solve this problem. The first way is, you know what, let's go ahead and determine how much calcium and fluoride ions are going to be allowed in solution. This is really a type 1 type problem, determining the solubility of a particular ion. Once we know the maximum solubility that we can have, we can compare it to what we do have and then see what happens. Well, kind of looking at this in the same kind of a way, but really putting a Q versus K comparison to it, what we're going to do is determine the calcium and fluoride again that we do have. That's again going to be something we still have to do for this first problem, and then use that to calculate Q and then compare that to K. Then we're going to do a Q versus K comparison. If Q is greater than K, that means we have more ions in solution that are allowed, so we're going to form a precipitate. If Q is less than K, that means we're still under the maximum limit, and so in that case, no precipitate would form. So there's going to be a commonality to some of the calculations and the quantitative piece to solving this problem in either way, but I'd like you to try to take a stab at working through either one of these. So pause the video and try to work through it, and then let the video play when you're either ready to check your worked out solution or to see either one of these worked out. Again, I'll give you a hint that the answer to the does it precipitate form is going to be an emphatic yes. Okay, so let's work through this first part. It says, let's determine how much is going to be allowed and compare it to what we have. So I'm going to break this up into two parts. I'm going to kind of start setting up the problem, and if you start seeing how the solution is supposed to be worked out, go ahead and pause the video and try to finish it again. So in this case, to figure out what the maximum allowed is, this becomes a type 2 type equilibrium problem. So again, we're writing our equilibrium expression. We've got what our KSP is equal to. And again, we're going to have some maximum allowable solubility. Remember, when we're having a solubility, we're solving for what X is. So we need to, in the rest of this problem here, solve for what the solubility is for each of these ions. We're solving for what X is. Then we need to say, well, what are the concentrations of solutions that we do have after we mix these two together? And this has to do with the fact that when we mix two things together, we're actually going to change the concentrations of those solutions because each of those solutions is diluting the other one. Remember, if we're doing a dilution, we could use this equation. So go ahead and see if you can finish this part of the problem by figuring out what are the new concentrations of calcium and fluoride ions after we mix these solutions together. Once you get the allowable concentrations and then the concentrations that we have, compare those numbers and see if we have exceeded the maximum allowable concentration. So again, here's working through what the maximum allowable concentration is. Just like we've seen for all of our type 2 problems, we're going to take our KSP value and we're going to solve for what X is. So X again is going to be the maximum allowable calcium concentration, so that's 2 times 10 to the minus 4th molar. To figure out the maximum allowable fluoride concentration, that's going to be double that value, so that's 4 times 10 to the minus 4th. So this is the concentration that would be allowed. Now let's go ahead and figure out, well, what is the concentration that we have? And we've got to do a dilution for that. So again, in this case, we're solving for M2. M1 is the initial concentration. V1 is the volume that we have of that. V2 for both of these calculations is going to be 300 milliliters because that's the volume that we have when we mix these together. Okay, so going through and finishing out this calculation, the calcium concentration after we mix things together, we had 100 milliliters that got diluted to 300, so that's essentially a 1/3 dilution, so we end up with 0.1 molar calcium ions. Going through the same type of a calculation for fluoride, it's essentially a 2/3 dilution of a 0.06 molar solution, so the final concentration of fluoride is 0.012 molar. In both of these situations, the concentration that we have of either of these ions is greater than the allowable limit, so we will end up with a precipitate. So for this problem, it was pretty straightforward because both of these ions exceeded their maximum limit. But I wanted to make sure to highlight for you, even if this was a situation where only one of the ions exceeded the maximum allowable limit, we still would get a precipitate in that case. It doesn't have to be both of them that are exceeding that maximum limit. So I'm going to run through the same sort of an analysis here, but doing a Q versus K comparison. Some of the calculations that we would have had to have done would be the same. We still need to figure out where are we at in order to figure out Q. So we'd still be doing these calculations to figure out the concentration of ions in our mixture. So again, we're going to see those numbers on the next slide here, and that's going to allow us to calculate Q. And then again, we need to do a comparison to K. So again, I'm going to set this problem up. If you want to try working through the solution on your own before you see the worked out solution, go ahead and pause the video in just a moment. But again, we need to see where are we at? What do we have? And so to figure out Q, we take the calcium concentration that we have in our mixture and multiply by the fluoride concentration in our mixture that is squared. That will tell us Q. And then we compare it to the K, which again was provided for us. Go ahead and pause the video if you want to try to work through those on your own before you see the worked out solution. So again, here are the values that we had from our previous slide here, right? Here were the worked out values that we had for our calcium and our fluoride ions in our mixture. Don't forget that we need to be squaring that fluoride concentration because that's what our equilibrium expression tells us to do. So again, here's our Q, 6 times 10 to the minus 4th. This is again where we are at. And we used the same values that we had to do, those dilution values that we used for the first way to solve this problem. And we need to compare this to K. So again, the K value is 3.2 times 10 to the minus 11th. This is a really easy comparison. Q is certainly much bigger than K. When Q again is bigger than K, that means we have too many ions in solution. We are greater than our allowable limit. So Q versus K, if Q is greater than K, we're going to shift to the left. And again, with this solubility equilibrium, that means we're going to be making more of the solid, which means we form a precipitate. So both of those ways to work through this problem highlight that in this situation, we have exceeded the maximum allowable ion concentration. So some of those have to come out of solution and go back into being a solid. All right, another problem to get us to practice this, but again, a molecular scenes problem. So remember, anytime you see a molecular scenes problem, you're probably going to need to be counting things. So we've got 4 molecular scenes here that each represent solutions of a silver carbonate solution. So silver is represented by this single silver covered sphere here, and then carbonate are represented by these polyatomic ions here. So the questions that we have here are, which scene best represents the solution in equilibrium? So if we had to predict which one of these most accurately represents a silver carbonate solution, which one would that be? Once we figure out which one represents the solution in equilibrium, we wanted to know in which of any of the other scenes will additional solid silver carbonate form. So if we know which one is at equilibrium, we can use that to solve for K. And then figuring out what Q is for the rest of these, then we could see if there's any other ones where Q has exceeded K and we're going to have a precipitate form. And lastly, this is sort of a qualitative piece. We'd like to think if we were to have a small volume acid that we added to our solution, how would that affect the silver concentration in scene 4, and again, the massive solid that's there? So if you want, go ahead and pause and try to think about the solutions for these 3 problems. So let's take these one at a time. And again, I've got the whole solution sort of revealed here. But if we're talking about silver carbonate, the first thing that's important to do, and I cannot highlight this enough with this part of this chapter, it is very important that you remember how to take a chemical name that's just written as a name, not a formula, and translate that into the atoms that you see in a chemical formula. So we need to remember that silver is going to be silver +1. Carbonate is CO3 2-, so that when this comes together to form an ionic compound, it's going to be Ag2CO3. So looking at that dissociating, it's going to dissociate into 2 silver cations for every carbonate anion. So if we take each of these solutions and we count the number of silver anions we have, and then the carbonate anions we have, we need to find something where the ratio is 2 to 1. In solution 1, it's actually backwards. It's 1 to 2. In solution 2, it's actually an equal ratio, and that's not going to work. And in solution 4, it's not a correct ratio either. The only one that has the correct ratio is solution 3, where we have twice as many silver cations as we have carbonate anions. Okay, so now that we know that this is our solution at equilibrium, remember, we're going to be looking at the rest of these solutions and asking if any of them are in a situation where we're going to have additional solid silver carbonate form, meaning we've actually exceeded and have too many ions in solution. So what we can do here is, since we know that this is the equilibrium concentration solution, we can use the numbers that we have there for ions in solution and use it to calculate what a K is. Now keep in mind, this is a hypothetical situation where we're just using a molecular scene to give a representative KSP. So this is not the actual value that you'd have for KSP. So counting the number of silver cations and then carbonate anions and putting them into our KSP expression, so we need to square the number of silver ions, we end up with K being equal to 32. So what we need to do then is take the rest of these and figure out, where are we at? What is the Q for the rest of these? So if you want, pause the video right now before you flip to the next slide and see if you can calculate what Q is for solutions 1, 2, and 4. Again, all we need to do to calculate Q is put these values into our KSP expression. So squaring the number of silver ions and then multiplying that by the number of carbonate ions. In solution 1 and solution 2, Q is going to be less than K, so those solutions are okay. We haven't exceeded the maximum allowable amount of ions. For solution 4, however, Q is going to be greater than K, and so in that case, we will see additional precipitate formed. So the last problem asks us to think about what would happen, and let's go back to the prompt here. Explain how, if at all, addition of a small volume of concentrated strong acid would affect the silver ion concentration in scene 4 and then the massive solid that's present. So in this case, or in fact any of these solutions where we still had some solid silver carbonate, by adding some acid here, that H plus is going to react with the carbonate anion in solution, forming a bicarbonate anion. And in pulling this carbonate out of solution, it's going to pull this entire equilibrium to the right, which means we're increasing the solubility of that silver carbonate. So let me make sure we answered all the questions there. We would increase the amount of silver that we'd have in solution, and we would decrease the mass of solid that's present, right? Because we're going to be pulling this equilibrium to the right, it's going to be increasing the concentration of silver, and we're going to be decreasing the mass of that silver carbonate because more of it is going to be dissociating into its component ions. All right, the last problem that we have to work on is what we call a selective precipitation problem. So basically, we are going to have multiple ions in solution here, and we're going to be adding a common ion that both of them would precipitate with, but sort of at different levels. Okay, so again, a solution of one of the precipitation ions is going to be added where we've got two ionic compounds that can be formed. What's going to happen is we're going to reach sort of that threshold to precipitate one of those compounds before the other one. That's actually going to allow us to separate one from the other. So again, the KSP of the less soluble compound is going to be greatly exceeded, so that one will precipitate. And again, we're going to allow for the maximum precipitation of this less soluble compound. So let's set up the problem here. And again, I encourage you to pause the video after we sort of set it up and have you guys think about working through the calculations. And again, you guys know I love pictures here to help explain things. So here again, we've got a solution that has 0.2 molar magnesium chloride and then 0.1 molar copper chloride. Remembering that all chloride salts are soluble, each of these solutions will have easily dissociated fully into its component cation, metal cation ions, and then chloride ions. Remembering that these chloride ions in this case are going to be spectator ions. Okay? I guess I probably should have said before, not necessarily all chloride salts are soluble, but many chloride salts are soluble. These two happen to be soluble. Okay, so again, the KSPs, when we add hydroxide, so generating magnesium hydroxide or copper hydroxide, both of those are going to precipitate, but they're going to precipitate at sort of different thresholds. So the KSP for magnesium hydroxide is 6.3 times 10 to the minus 10th. For copper hydroxide, it's 2.2 times 10 to the minus 20th. So if we ask the question, who is less soluble? Who is less soluble is the salt that has the smaller KSP value. So this kind of represents a kind of problem that you might see on, say, part 1 of our exam. I might give you two salts, and knowing what the KSP values are, I'll ask the question, who is more soluble or who is less soluble? The one that's less soluble is the one that has the smaller KSP value. In this case, it's going to be copper hydroxide. So copper hydroxide, again, having the smaller KSP, as we start adding in hydroxide, as soon as we reach that guy's threshold, we'll start precipitating that. And that will be the only one that precipitates until we reach the threshold for magnesium. So the question becomes, how much hydroxide can we add that will allow us to precipitate the most copper and then not precipitate magnesium? Because doing that is going to allow us to separate these ions, because the copper hydroxide will get pulled down as a precipitate and come to the bottom of our container, and then the magnesium will still be as an ion in solution. So if you want, take a stab at thinking about how you might figure out what's the maximum amount of hydroxide that I could add that would not precipitate magnesium, but that would precipitate copper. All right, so I'm going to set up this problem a little bit for you, and then again, if you want to pause it again and try to finish working through it, I would encourage you to do that. So again, asking this problem another way, what is the hydroxide that would be needed to precipitate magnesium hydroxide? And again, if we add just under that amount, that's going to precipitate the maximum amount of copper. Okay, so we could really ask then, what's the solubility of magnesium hydroxide? That's kind of a type 2 equilibrium problem. We're asking what X is. Okay, so again, this is the equilibrium that we're concerned with. And again, the KSP is what's given here. The value was provided. And again, it's going to be equal to the magnesium concentration times the hydroxide concentration squared. I'm going to make sure to point out a really important thing and a common place where a student could make a mistake with this problem. When you're doing your ICE table, remember that we've got some of that magnesium that's already sort of filled up because we started with magnesium chloride and then we were adding in hydroxide. So we want to know, what's the amount of hydroxide that we'd need to add? What is this number so that we would end up pushing this equilibrium back this way and making some precipitate? So I encourage you, pause the video right now, see if you can figure out what is this hydroxide concentration. So again, figuring out what the hydroxide concentration is really is just solving for X in this problem. Now again, the main difference is we've already got some magnesium that's in solution from that magnesium chloride. So this is not going to be just an X, it's a 0.2 plus X, and then we've got 2X, that quantity squared, equal to the KSP. So this becomes kind of like a common ion problem. We have to make an assumption to make our algebra easy here. So it's going to be 0.2 then times 4x squared. Solving for x gives us 2.8 times 10 to the minus fifth. And this again is just reminding us for this guy. Remember that magnesium cup was already somewhat filled from the magnesium chloride that we have. So the maximum amount of hydroxide that we could add before we would exceed our KSP is going to be 5.6 times 10 to the minus fifth. Remember, this is what x was. Solving our KSP expression is going to allow us to solve for x. To figure out what the hydroxide concentration is, we'd need to double that. So that's why we have 5.6 times 10 to the minus fifth. So said another way, this is the maximum amount of hydroxide that we could add before we would start precipitating magnesium, because this represents the maximum allowable amount of hydroxide. So if we are just under this, we will be doing the maximum precipitation of copper hydroxide because we will well have exceeded that maximum capacity. But again, we won't be touching any of the precipitation of magnesium yet. Just one last little piece to highlight. If I wanted to add one extra layer to this problem, something else that we could do here is I could ask the question, what is the pH that you'd need to be at? How basic could you make the solution and selectively precipitate the copper but not magnesium? And all you'd have to do there, if this is the maximum allowable hydroxide concentration, negative log of that would give you pOH. Subtract that from 14 to give you pH. That's the highest pH you could be at and safely only precipitate the copper hydroxide. If you increase the pH anymore, you're going to start precipitating the magnesium hydroxide because you will have exceeded that allowable amount of hydroxide. All right, so that wraps up our last lecture here in Learning Unit 7 on complex ionic equilibria. Okay, so lots of homework problems to practice all of these concepts. The main two things that we talked about here, I should say 3 things in this chapter. So we talked about buffers, we talked about titrations, and then we talked about solubility or sparing solubility of salts that we sort of said were insoluble in Gen Chem 1. So we'll take some time and we'll also practice some more problems with our activity that we'll work on in class, and then that will wrap up everything for this Learning Unit 7, and then we will be ready for our next exam, which is again on Learning Unit 6 and 7, so chapters 18 and 19.